In today's video, we are going to look at two topics, solving radical equations and graphing radical functions. So in our first piece, let's look at the equation part of this. And so when we're solving radical equations, we want to be very careful when we come up across a problem that has an even root. So our index is even, like a 2 or a 4 or 6, etc. And the big thing is when we were looking at these types of problems, we cannot take an even root of a negative number without getting complex answers. And what we're focusing on with solving these equations is what's going to really work with the function. And thinking of graphing these functions out, do we ever graph complex numbers? We do not. So we are going to be looking for anytime we have real answers. So we cannot have a negative number kind of equaling an even root in these problems. Now, we may mathematically still be able to work through a solution, but this is where it's going to be super important for us to always check our work on all of these problems, because sometimes we're going to have something called an extraneous solution, or in other words, a solution that comes out of the algebra but still doesn't work with the equation. So if you're curious, I have an extra video posted on extraneous solutions from Khan Academy that you can definitely check out for some extra examples on, why do some of these solutions that come out not work? When we were solving out these problems, we're going to use, typical equation solving practice, kind of like when we did absolute values. So when we solve things out, we always try to get the absolute value expression, or today that's going to mean the radical expression or the expression raised to a rational exponent. Try to get that by itself first. And then you're going to kind of undo your radical. So if we had like a square root, we're going to square both sides. If we had it raised to a 1/2 exponent, we raise both sides to the 2, to the reciprocal exponent, to undo that exponent. Then we'll be able to solve out for our x. And then we always want to check our answer to make sure we haven't gotten an extraneous solution. So let's check these out. First problem. So first off, isolate the radical. So we need to get the expression square root 9 minus 5x totally by itself. First thing we're going to do is add 2. So we're going to have 9 minus 5x on the left. Adding 2 to both sides, we have an 8. And so right off the bat, I know I'm in a situation where I'm going to have my solution. I do not have my radical equal to a negative number. So let's now undo the radical, which means I'm going to raise both sides to the reciprocal exponent, which is 2. So squaring both sides, again, that's going to undo our radical. So we'll have a 9 minus 5x. On the right-hand side, that gives us a 64. And now we can just keep solving out. So subtract a 9 from both sides. We're going to end up with 55. And divide your -5 from both sides equals a -11. So now let's go through and check our work. So again, keep in mind, I did not have a radical equal a negative number, but I still got out a negative answer. As long as I check my work and everything checks out, I'm still good to go. So plugging into our original problem, and let me change my color. So let's do -2 plus square root of 9 minus 5 times -11. And I want to check to see if that comes out to be -6. So multiplying out, we have a -5 times -11, which ends up being a positive 55, which is going to work out really nicely for us. So -2 plus the square root of 64, aka -2 plus 8, comes out to be 6, which checks out. So that means our solution is indeed x equals -11. Alrighty. Problem number 2, technically a radical in disguise, because what does that 1/3 exponent mean from our last video? Yeah, it's really cube root. So eventually when we do this problem, we're going to have to do the raise to the reciprocal exponent on both sides. In other words, raise both sides to the 3, cube both sides, and that will undo that grouping. But first we got to get the group by itself. So I'm going to start by subtracting a 5 from both sides. Now that gives me a -5 on the right-hand side, but I do not have an even root. I have an odd root. I have a cube root. So I shouldn't need to worry about it. I'm still going to check my answer at the end just in case. So to get at that y, to undo that 1/3 exponent, again, I'm going to raise both sides to the reciprocal exponent, aka 3. That'll undo my cube root. Okay, so that leaves me with just a 3y plus 1 on the left. And then if you plug this in the calculator, you want to be careful that you include those parentheses. And that's going to come out to negative 125. Alrighty, keep going. So move the 1. So we'll have a negative 124. And then divide through both sides by 3, and we're going to get a negative 41.3 repeating. So let's check this out. So if we're going to plug in 4.1 or 41.3 repeating, that means you want to type in a whole bunch of 3s, no matter what calculator you're using. So plugging back in, we have 3 times negative 41.3 repeating plus 1 raised to the 1/3 power plus 5. Alrighty. So let's see, I know 3 times negative 41.3 repeating, well, that's just that negative 124. That's just using my math that I already did. And as long as I was accurate on my calculator, I'm good to go. So that would give me a negative 123 raised to the 1/3 power. And so plugging that in your calculator, again, you can just use the caret key and then type in your fraction. If you're going to try to do this with a decimal, again, 0.3333333, whole bunch of 3s to make sure that the calculator understands the pattern you're trying to use. That should come out to be approximately negative 4.97, but that's not really what we want, is it? Let's see, let me double check. So negative 123 raised to the 1/3 power. And again, because we're probably dealing with, weird values in here and calculator running or rounding off, I'm actually getting negative 4.97 and continued decimal, but that's probably because we're trying to take that weird cube root. Plus 5, well, negative 4.97, pretty darn close to 5. So I'm going to say that this one checks out. Alrighty, number 3, 6th root of 4x plus 1 plus 4 equals negative 1. So first thing is isolate that radical. So we need to subtract the 4 from both sides. So 6th root of 4x plus 1 equals negative 3. Wait a second. I told you that an even root is not going to work, but I don't want you to just believe me. So let's go through and see what happens when we check our answer on this. So 6th root means I have to raise both sides to the 6th, or raise both sides to the 6th power. Okay, and so that cancels out my 6th root. Negative 3 raised to the 6th power is going to be a large number, positive 729. Again, be careful using your parentheses on your calculator. And then get your x by itself. So subtract the 1, divide both sides by 4, and it actually gives us this pretty nice number, 182. So let's plug that back in and check our work. So we have 6th root of 4 times 182 plus 1 plus 4, and the whole thing's supposed to come out to 1 eventually. Now I know 4 times 182, that's the 728. I don't need to go back to the calculator to do that. And that gives me the 6th root of 729 plus 4 plus 4. And I already know that the 6th root of 29, well, wait a second. When I plug that in my calculator, I don't get out a negative 3. I get out a positive 3. And positive 3 plus 4 equals 7. It doesn't equal negative 1. So unfortunately, this one won't check out in every single scenario. When we do a square root, technically we have to consider plus and minus, but if it doesn't check out in every possible scenario, it's not a valid solution. So this is one of our extraneous solution problems. This one does not check, so I have to throw out my only answer that worked. So this one, unfortunately, is no solution. And in the second half of the video, we're going to come back and think about the function and why that's actually happening. But 2 more solving examples. Okay, number 4. So this one looks a little different. We have square roots on both sides, but again, if I want to undo a square root, just raise both sides to that reciprocal exponent. So Square root is really raised to the 1/2. Reciprocal of 1/2 is 2. So I'm going to square both sides. I have to include that 2 coefficient in there as well. So on the left, I'll get x minus 5. On the right-hand side, 2 squared is 4. And then I have the x plus 1. So distributing out, I have 4x plus 4. Combine my like terms, add a x to both sides, I have a 5x. Subtract a 4 from both sides, I have a negative 9. Excuse me, I'm subtracting that x, so that's actually a 3x. And then divide both sides by 3, I get a negative 3. And again, negative answer, okay, that might work. Let's check our work and see what happens. So we have a negative 3. Ooh, I'm already seeing a problem here. So negative 3 minus 5 under the square root, and then 2 root negative 3 plus 1. And here's the problem. When we're solving our solution, our radical equations, again, we're trying to justify this and make this work within what we know about this function. And if we're not dealing with imaginary numbers in this function, then we shouldn't have imaginary numbers coming out in any way, shape, or form in this problem, whether we're checking it or not. And as soon as I simplify out that negative 3 minus 5, I'm looking at square root of negative 8, which is definitely an imaginary number. Same thing on the right-hand side, square root of negative 2, imaginary number. And yes, they check out with each other, but because we're dealing with complex and we're not supposed to deal with those complex when we're looking at this function, that means this unfortunately is another no solution problem. We should only be dealing with real solutions, real values. So officially, this is no real solution that still yields a real value to those functions. Okay, and then number 5. So first off, again, isolate your radical. So we're going to have 4th root of x plus 5 equals positive 2. We have a positive number, so this one should work. Okay, raise both sides to 4th power, or power of 4, to undo that 4th root. Okay, so we just have an x plus 5 on the left, 2 raised to the 4th power, 2 times 2 times 2 times 2 gives us 16. This is a really nice answer to work with, just an 11. So let's plug it in and see what happens. So 4th root of 11 plus 5, and then minus 2 should end up coming out to 0 if this checks. And 4th root of 16, we already did the math. We know the 4th root of 16 is indeed 2, and 2 minus 2 equals 0. So this problem checks out. So be very careful on solving radical equations. You want to check your work on every single step. Even if you think you get what looks like a correct answer for it, it may not work with that function. So go ahead, pause the video, try out problems 6 and 7. And then come back and we'll look at some graph properties, which will connect to why we can't use some of these solutions that we might come up with. Alrighty, so now looking at rational graphs. So we looked at these very briefly when we did our function families all the way at the beginning of the year in Unit 1. And so this graph probably looks a little familiar. We can use all of our same transformations that we did before to predict where this graph is going to go. But keep in mind with these graphs, can we use every single x and every single y? So looking at our example graph, find the domain of f of x equals square root of x plus 3 minus 2. Well, keep in mind that plus 3 is really moving our graph to the left 3 units from the origin, and the minus 2 is moving it down 2. And so it starts at a very specific point at negative 3, negative 2. But I don't have anything to the left of that graph. So I can't use every single real number on this. So when we were talking about our domain and range on that one, technically we had a restricted domain. We can't use every single x. And so that actually does relate back to our problems that we were just solving out. If we come up with a solution that doesn't fall within that domain, it's not a valid solution. And so that's why some of those numbers that mathematically look like they came out correctly really didn't, because if we compare that back to the domain of that function, things are going to go screwy. So we actually have a way to find that domain without even having to graph it. So if we look at just that value under the radical, if we're trying to deal with real numbers, we know that that needs to be a positive number. So if you take that expression, just the piece under the radical, and set it so it's greater than or equal to 0, solve it out for the x, that's going to be your domain. So checking against the example, if we do this with the x plus 3 and solve that out, we get that x has to be greater than or equal to -3. And looking at our function on our graph, again, if we look at that -3 x value, we don't have anything to the left of that at all. So that is our restricted domain. Technically, our domain would be all x's such that x is greater than or equal to -3. So keep that in mind. And when you're using this technique to find your domain, don't forget your inequality rules. So you're always going to remember to flip the inequality symbol anytime you might need to multiply or divide by a negative number. And they will happen sometimes. All right, so 8 and 9, let's just figure out our domain without even looking at a graph. So here we go. So all I'm going to do is take whatever's in the radicand, set it so it's greater than or equal to 0. So x minus 1 greater than or equal to 0, and then solve that for the x. All I have to do is add a 1, don't have to multiply or divide by a negative, and so that means my domain is going to be x is such that x is greater than or equal to 1. Same thing for number 9. Only look at the radicand. That's the only place where this function might fall apart, is if we have negative values underneath that radical sign. So again, subtract 5 from both sides. So that means our domain x is such that x is greater than or equal to -5. And so we can think of this in terms of our values on the graph as well. So let's go ahead and graph a couple of these out, look at our characteristics of our graph, and think about how that domain is going to affect things. In number 10, we have the function f of x equals 2 square root x plus 2. So before I go over to Desmos to check my work, again, let's use our properties that we talked about in our first unit when we were talking about function families. So I know the overall shape of this, for any radical graph, it starts at a point and keeps going. So that point where it starts, I know from that plus 2 inside the radical, I'm going to have to move the entire graph to the left 2 units. Excuse me. And then the only thing to deal with now is the 2 that's out in front in the A position. So because that's not negative, I know I don't have to flip or do anything with a graph like that, but I do need to have a vertical dilation of 2. So every y value is going to get stretched out twice as far from the x-axis as we would normally expect. So from the starting point, if I went over 1 space, my square root of 1 to plug into the function would be 1. But I'm not going to go up 1. I'm going to go up 1 times 2, aka 2. Next perfect square is 4. So over 4 spaces from our starting point, square root of 4 is 2, but 2 times 2 is 4. And so let's pop over to Desmos to see if my graphing was correct. And I have actually already graphed that out. There's Desmos. And we can see I have my x-intercept of -2, 0. We don't have the greatest y-intercept on this one, but it's not a bad point. We can still see where that is. And we definitely predicted correctly with the point at 2, 4. So right around there. Alrighty, so back over to our example. So our transformations that happened, we had a vertical dilation of 2. So we multiplied every y value times 2, made it look twice as tall as it should be. And we also moved everything to the left 2 from that plus 2 inside the function. Our domain and range, well, we only start at that point, -2, 0. So those are kind of the restrictions on our domain and range. Our domain, our x's start at that -2, and we use everything that's bigger than or equal to -2. Same thing for our range. our y value at our starting point, -2, 0. Y value is 0, and we want everything above that. So f of x is such that f of x greater than or equal to 0. Our x-intercept is just that main kind of vertex point of -2, 0. Our y-intercept, again, not the prettiest point, but if we go back to the coordinates that we saw on Desmos, we had that hitting at 0 and approximately 2.83. All right, minimums and maximums. We only have one minimum on this graph. Our starting point is the lowest point on the graph. And again, we had slightly different notation for this. Our minimum value of y is 0, and that happens at x equals -2. And I'm going to go ahead and circle that because that is an absolute minimum for this graph. That is the lowest, absolutely lowest point that we can reach. Now, in terms of maximum, if our graph keeps going over and up and over and up and over and up and over and up, it's never actually going to reach a maximum value. So this one has a none. Same kind of thing, intervals of increasing and decreasing are a little different. If we think in terms of, again, we start walking on our graph, and in terms of which direction we're walking and are we going uphill or downhill? Well, as I start walking, I'm definitely going to be walking uphill. And so that means from the start of my graph, I'm going to be increasing. Our graph starts at our x value of -2 and then keeps going towards infinity. But will we ever walk downhill if we're walking left to right on our graph? Unfortunately not. So there's no interval of decreasing. Same sort of thing for end behavior. We have to tweak it a little bit because as we think of walking left versus right on our graph, well, as we walk to the right, as x approaches positive infinity, well, our graph will just keep going in that up direction. So as x approaches positive infinity, our y values keep going up. So f of x approaches positive infinity as well. But if you move to the left, so if we're walking in the other direction, we hit a stopping point. So we don't actually ever get to x approaches negative infinity. It's never going to get there. So we actually throw out that end behavior and we only state as x is approaching infinity what that behavior is. So none or does not exist. Alrighty, so at this point would be a great time for you to stop the video. I am going to stop recording, but try the rest of the problems out and then check the filled in organizer that is posted right below this video. And as always, let me know if you have any questions or concerns, especially before you attempt your mini quiz on this material. Have a great rest of your day.